Okay, so today I want to justify, some of the facts that I assumed in a spectral sequence. Okay, so in the ray spectral sequence, the E2 term is the check homology HP of an open cover with coefficients in HQ. Right. Okay, this is for a map. Okay, where HQ is the pre-sheaf HQ of U is the cohomology of the inverse image of U. Okay, so is the pre-sheaf on the open cover X. On the open cover U of X, yeah. So what we would like to do is to simplify this check cohomology. Okay? So we said that in case, this should be y to x, right? The base is x. In case x is simply connected, and if this is a fiber bundle, yeah, let's leave. I'll leave it as a map here. But if it's a fiber bundle with fiber F, then this is a tensor product of the cohomology of the base with the cohomology of the fiber, right? So we assume that. So today I would like to study this pre-sheaf, okay, and see how it could be used to simplify this expression. Okay, and so what I'm going to do now is just combinatorial algebraic topology, okay? Because we're going to associate to an open cover its nerve, and the nerve of an open cover is a simplicial complex. Okay? So we want to define what's called the edge group of the simplicial complex, which is the analog of the fundamental group of a topological space. Okay, and so let me start by defining simplicial complexes. So I first define a simplex. That's an example of one simplex. And then this is an example of a two simplex. A one simplex is basically an edge. A two simplex is a triangle. A three simplex is a tetrahedron. Okay, so a P simplex spanned by P plus 1 points, V0 to VP, it's basically, it's all the convex linear combinations of these points, but these points have to be in general position, okay? Well, that just means like if you have 3 points, they can't be collinear, okay? And so general position really just means that if you fix one of the points, then you get vectors coming out of that points, and they're linearly independent. So these points are in general position if V1 minus V0 to VP minus V0. Oh, and this is in Rn, right? The points are in Rn. So these vectors in Rn are linearly independent. Okay? So that's what it means to be in general position. And then the P simplex, we denote by A, and that's the simplex spanned by V0 to VP. And that is the set of all convex linear combinations. So that means TIVI, I goes from 0 to P, okay, such that the sum of TI is 1. And the TIs are all greater than or equal to 0. Okay, okay, so that's a simplex. And now, a face of a simplex like this, that's a face of this simplex, or this is a face of a tetrahedron. It's just a simplex spanned by a subset of the vertices. Okay, so a face of a P simplex is a simplex spanned by a subset of V0 to VP. Okay, and then a simplicial complex is just a collection of simplices so that they intersect in a nice way. So that's one simplex, and that's another simplex. Okay, but they have to intersect in a face. Okay. So that's an example of a simplicial complex. Okay. And then if it contains a simplex, it has to contain all the faces. Okay. Yeah. Right. Yeah. Yeah. Because like, like how do I distinguish these two simplices? Okay. This one has this face. This one, it doesn't have this face. So you have to, in the description of a simplicial complex, you have to write down all the faces too. Okay. So let me see. Yeah, so definition, a simplicial complex K is a collection of simplices this is in Rn. So a collection of simplices in Rn such that every face of a simplex in K is in K. And then 2, the intersection of any two simplices the intersection of any two simplices is a face of each of them. Okay? So that means, like, you can't have yeah, like you can't have this. That's not a simplicial complex, okay? Because the intersection of these two simplices is this, and that's not a face of either of them, okay? So this is not a simplicial complex, okay? This is not. Okay? And so now let me define the edge group of a simplicial complex, which is going to correspond to the fundamental group, okay, of the topological space, that is the union of all the simplices. Okay, so the edge group of a simplicial complex. Okay? And okay, so instead of a curve in the topological space, we define an edge path. An edge path in K, well, it just means you travel along the edges. Okay? So an edge path is specified by a sequence of vertices. So an edge path in K is a sequence of vertices V0, V1 to Vk in which any two consecutive vertices is either an edge or they could be the same. Okay, so in which either Vi equals Vi plus 1 or Vi plus 1 is an edge. Okay, now because this sequence has an order, so an edge path has a direction, right? You're going from V0 to V1, and then V1 to V2, and so on. Yeah. Oh. Yeah. So like, okay, that would be an edge path. and it has a direction. Okay. Now, an edge loop is when the initial point is equal to the end point. Okay. Okay. And you can multiply two edge paths by following one with another. So the product of two edge paths, say V0 to VK and VK to VL is concatenation. Okay, concatenation means you follow one with the other. So V0 to VK times VK to VL is V0 to VK and then VK to VL. Okay? You can have the two being the same. That just means that maybe you stay there for 1 second. So you notice in order to define a product, the endpoint of the first edge path has to be equal to the initial point of the second edge path. Okay? Okay. So okay. Okay, so there are three basic types of equivalence relations. If you have an edge path in which two consecutive vertices are the same, then this is equivalent to just one V. Okay. And if UV is one simplex, then whenever you have UV, UV just a minute, UVU, UVU, okay? So that means you go to V and then you come back to U. Okay, whenever you have UVU in your edge path, well, that's equivalent to just U. And if you have a two simplex, UVW, you have a two simplex, then when you go from U to V to W, that's the same as going from U to V, U to W. Okay? Yeah, so this is the homotopy relation. Right? If you have a two simplex, then UVW, that path is homotopy equivalent to UW. Okay, because in the topological category, you can move this curve, right, through that two simplex to this curve. Okay, so in this case, UVW is equivalent to just UW. Okay? So we have these three equivalence relations, and we look at we have these three relations, and we can let them generate an equivalence relation. Okay. So let's see. So here's an example. Let's say you have V0, V1, V2, V0. Okay, and you multiply it by V0, V2, V1, V0. Okay? So you have concatenation. So that means you write down everything. Okay? But then you will have V0, V0. So V0, V0. Oh, just a minute. V0, V0. Oh, right. Yeah. Yeah. So V0, V0 is V0. I'm trying to show that this is inverse to that. So, yeah. Okay. So, okay. So this is going to be equivalent to, now, so V0, V0 is just V0. And what's V2, V0, V2? Right? I mean, V0, V2 is an edge. So if you do V2, V0, V2, that means you're going V2, V0, V2, okay? So that is just gonna be V2. And then you have V1, V2, V1. What's V1, V2, V1? So yeah, let's V0, V1, V2, V0, V2, V1, V0. And then, okay, so this is just V2. That's equivalent to V0, V1, V2, V1, V0. And this V1. So this is V0, V1, V0, and that's equivalent to V0. Okay? Yeah. So what that means is that if you write down any edge loop, it has an inverse, okay, just by reversing the order under this equivalence relation. Okay? Yeah, so the edge group is defined to be all the edge loops modulo this equivalence relation. Okay? The edge group of okay, the edge group of a simplicial complex K with a base point V0 is the set of equivalence classes of edge loops at V0 yeah, under this equivalence relation with product with concatenation as product and V0 as the identity and the inverse V0, V1, Vk minus 1, V0, the inverse of a loop, it's just the loop written in the reverse order. Okay? So that makes it into a group, the edge group. Yeah? Okay. Let's calculate a couple of examples. So suppose this is your simplicial complex. V0, V1, V2. And we want to calculate its edge group. Based at V naught. Well, you have this loop, right? V0, V1, V2, V0. Yeah. And that's, yeah, that can be simplified. And you can go around this triangle infinitely many times. So if this loop is 1, you can go around twice, you get 2, and then 3 times 3. And then you can go in the opposite direction. You get -1, -2, -3, and so on. So the edge group is Z. Okay? So we're generated by V0, V1, V2, V0. Mhm. All right, and let's look at another example. So now we fill this in. Okay, now if you start here, well, then you have to go clockwise or counterclockwise. Let's say we go clockwise. That gives us a loop. Okay? So we have V0, V1, V2, V0. But you have a two simplex. When you have a two simplex, then V0, V1, V2, V0, V1, V2 is the same as V0, V2, right? Sorry, in here, yeah, V0, V1, V2, that's equivalent to V0, V2. Okay, so as the equivalence class then is equal to V0, V0, V1, V2 is V0, V2. Okay, and then V0. Okay. But V0, V2, V0, that's V0, V2, V0. Okay, so that's equal to just V0. The identity. Okay, so I mean, this is the one path. You can go in the opposite direction. Okay, that's also the identity, and you go 3 times around, it's still the identity. So in this example, then the edge group of KV0, is just the identity. So it's trivial. Okay? Yeah, so so you see that it does calculate the fundamental group, of the topological space underlying the simplicial complex. Okay, so that is just combinatorial topology. Okay, now let's go back to pre-sheaves. Okay. Now, there is a special kind of pre-sheaf that is called constant pre-sheaves. Okay. And then I'm also going to define something called locally constant pre-sheaves. The definition of the constant pre-sheaf is standard. So a pre-sheaf F on a topological space X is constant with group G if for every open set U in X, f of U is G, and for an inclusion of open sets, the restriction from f of U to f of V, this restriction, well, that's a map from G to G. It's the identity. So that's a constant presheaf. Now, if you have an open cover, you can also define, a presheaf on the open cover, right? So, yeah. So let me use this board. Yeah. Okay, so now let U be an open cover of X. So a presheaf F on U is constant with group G. Okay? So it's given by the same definition, except now the open sets are finite intersections of the open sets in the open cover. Right? So by the same definition, but with U in open U, and that means non-empty finite intersections of open sets in the cover. Mhm. Okay, and then so let's look at this example. So let F of U be locally constant functions. From U to G. Is this a constant presheaf? What do you think? Like on every open set, is it G? If it's locally constant. Oh, well, okay. To talk about Now, locally constant, do you need a topology on G? Let's just change this to R, okay? Just to make it simpler. I looked at locally constant real value functions. So is it true that on every open set, then you just get R? Hmm? If? Yeah, that's right. I mean, if U has two connected components, then the set of locally constant functions would be R plus R, right? Because you can have a different constant on each component. So, yeah. So if U has two connected components, then f of U is R plus R. And if U has one connected component, then f of U is just R. So yeah, so this is not so locally constant with group R. So F is not, or it's not constant with group R. Okay. Okay. It's not constant with group R on, so this is on a topological space X. But if you look at just a good cover, is it constant? Is it a constant pre-sheaf? Oh, okay. Now for a topological space, what's the definition of a good cover? Well, you know, for a manifold, we say that all the finite non-empty intersections have to be diffeomorphic to Rn. But for a topological space, you can't talk about diffeomorphisms. So for a topological space, you need a different definition of a good cover. And the definition is that all the non-empty finite intersections are contractible. Non-empty finite intersections, so that means all U in open U, I define open U here, non-empty finite intersections are contractible. Contractible means having the homotopy type of a point. So in particular, a contractible topological space is connected. Okay, and now let's look at the same U is F constant with group R on U. Okay? So I'm looking for a yes or no answer. And I want somebody to talk other than Su Ping Chen. Or maybe I'll take a poll. How many people say yes? It's either yes or no. If you say yes, you raise your hand. Yeah. Uh-huh. Okay, good. Yeah. It's yes. Because every finite intersection, every non-empty finite intersection is contractible, so it's connected, and a locally constant function on a connected set is constant. So the group is R, okay? And then the restriction, well, it's the same constant, right? So it's, the restriction is the identity. Okay, so yes, yeah. Uh-huh. Okay. So this is good because then it is this pre-sheaf R bar, right? Uh, and we saw earlier when you calculate check cohomology with coefficients R bar, you get the de Rham cohomology. Mhm. That's the check de Rham isomorphism. Yeah. So we would like our sheaves to be isomorphic to the constant pre-sheaf R bar. Okay, and so far that's constant pre-sheaf. And now let me define a locally constant pre-sheaf. Okay, this definition is not standard. I have not seen it anywhere, but it's a useful definition. And I think it's not in the literature because I think people usually define cohomology, check cohomology using sheaves. They don't look at pre-sheaves. But as you have seen, you don't need sheaves. All you need is pre-sheaves. Okay? So nobody else does it this way. And that's why they don't define locally constant pre-sheaves. Okay, so a pre-sheaf F on a topological space X is locally constant with group G if for all U open in X, F of U is G, and for all V contained in U that are open sets in X, so far, it's exactly the same as the constant pre-sheaf, but now the restriction, instead of being the identity, it's just an isomorphism. So the restriction from FU to FV, and both are G, right, is an isomorphism. Okay? So you don't require it to be the identity. So let me give you an example of a locally constant pre-sheaf that's not constant. Oh, yes. And then, of course, you can define it on an open cover, right? In the same way. Okay. So example, locally constant presheaf that is not constant. So let's say this is the nerve of an open cover. And so a presheaf associates to each open set a group and each non-empty intersection a group. And so let me see. Yeah. Sorry, I should have written down the open cover first. So let's say you have a circle and then you have a good cover. Okay. So U0, U1, U2, and this is the nerve, right? You got 3 open sets and then 3 non-empty intersections. And so a presheaf associates to each open set a group and each intersection a group. Okay, yeah. So this is actually say f of U0 and this is f of U2 and this is f of U02. Okay. And so you have restrictions going this way. Okay. And okay, you can have these restrictions as identity and except for this one, make it -1. Okay, so it's an isomorphism. Yeah, so this picture is a presheaf on the open cover. And these are the restriction maps. And you see that, well, the restriction maps are all isomorphism, so it's locally constant, but it's not constant, okay? Because not all the restriction maps are identities. Okay, let's take a break for 10 minutes, and then we'll continue with this. Okay, now because U has only 3 open sets, okay, the nerve has only 3 vertices. But the presheaf should associate a group not just to the open sets, but also to the non-empty finite intersections. And so you also need to take these edges that represent the non-empty finite intersections, okay? So, but on each edge, we pick the midpoint to represent it. And this picture with 6 vertices is called the barycentric subdivision of the triangle. Okay? So, yeah, so let me define what that is, okay? So first, we'll define the barycenter of a simplex. Yeah, we're gonna define the barycentric subdivision of a simplicial complex. And we start with the barycenter of a simplex. The barycenter of a simplex A okay. Well, now in physics, it's the center of mass. Okay? So, I mean, if your plate is has uniform density, then of course the barycenter of an edge is going to be its midpoint. Okay? And the barycenter of a triangle is its centroid. You know, it's an important point. It's the intersection of all the angle bisectors. It's also the intersection of all the, yeah. Okay, yeah, well, anyway, it's the center of mass, okay? So, yeah, so the barycenter of a P simplex is given by this formula, 1 over P plus 1, the sum of V I goes from 0 to P. Okay? So if you have 2 points, then P is 1, then you have 1/2 of V0 plus V1. Okay, so in general, that's the formula for the barycenter. Now, if you have a vertex, then you have V0. So you just have 1 term V0 divided by 1. So a vertex is its own barycenter. And then the barycentric subdivision of a simplicial complex is obtained by, you know, like subdividing each simplex using all of its barycenters. Okay? So definition, the barycentric subdivision of a simplicial complex K is the simplicial complex K prime obtained from K by subdividing each simplex using its barycenters as the new vertices. Okay? So to subdivide this triangle, I mean, you first, okay, subdivide each edge using its barycenters as vertices, and then you subdivide the triangle, okay, using all the new vertices, you know, all the barycenters as new vertices. Okay? I mean, these all vertices, they are their own barycenters, so they're also included in the new vertices. Okay? Yeah, and so that's how you divide a p-simplex. And then if you have a simplicial complex, it's a collection of p-simplices. So you just divide each of them. Okay, yeah. And then you get the barycentric subdivision. So, yeah. Okay, so like here, let me see. So this one, if this is U alpha, this is U beta. Okay, this is U alpha beta. And this would be U alpha beta gamma. So yeah, if you have a nerve, okay. So if the nerve, you know, is a two simplex, then this would be the barycentric subdivision of the nerve. It's a new simplicial complex with more vertices and faces. And you see that here, you know, each of the new triangle, in each of the new triangle, so you have these three vertices, and so one of them, yeah, so this is contained in this as an open set, and this is contained in this, okay? Yeah. So in every triangle, there is a containment relation among the three vertices. Okay? Because if it's a barycenter, then it's a it's an intersection, so it's a subset. Okay? So, yeah. Yeah, so what I want to say is this proposition, yeah, um, how do I say? I mean, okay, so to specify this triangle, I specify its 3 vertices, but yeah, because a simplex is specified by its vertices. Okay, but if I just put them in an arbitrary order, there, you know, there may not be a containment relation. Okay, so what I want to say is that so let U be an open cover of some topological space X, and N of U, its nerve. Then you have a simplex so a simplex is in the barycentric division if and only if there's a permutation sigma of the numbers from 0 to p such that you have to have a containment relation. So U sigma 0 is contained in U sigma 1. It's contained in U sigma p. Okay. Yeah. Yeah. So these 3 vertices may be given in an arbitrary order, but there has to be an order in which you have this containment relation. Okay. And now a pre-sheaf on an open cover okay, is simply an assignment of a group to each vertex of the barycentric division of the nerve. Okay. Oh gosh. So Okay. So, because the the berry centers are precisely the non-empty intersections. Alpha, beta. Um, Now, if the, so like here, this is a subset. This is a triple intersection, is a subset of the double intersection, is a subset of U alpha. So the restriction map goes this way and then this way. Right? But if you have a locally constant pre-sheaf, these restriction maps are isomorphisms. So actually they can go both ways. Okay? So yeah, yeah. So if F is locally constant on an open cover, then rho of UV and if V is is a subset of U, so we can define rho of VU, which actually you can't think of as a restriction because V is a subset of U, but rho of UV is a restriction, but because it's an isomorphism, you can take its inverse. Okay, so you can define rho of VU, even though V is contained in U. And what that means is that in this picture, the arrows can go both ways. Okay. So then you don't have to worry about whether, like one open set is a subset of another. Okay. Yeah. Yeah. So then, if you have a path, then you have an isomorphism. So a path, let's say V0, V0, V1, Vk, okay? So a path in the barycentric subdivision, yeah, defines an isomorphism from f of V0 to f of V1 to f of Vk, and this would be rho V0, V1, rho V1, V2, and so on. And these are all isomorphisms. And it doesn't matter whether V0, V1 is a subset of V0 or not. Okay? So any path will define an isomorphism. And so then a loop will go back to itself. So a loop will define an automorphism. Yeah. So uh, an edge loop of the first the barycentric subdivision of the nerve at U0 defines an automorphism of f of U0. Yeah, you'll go from U0 to U0. Okay. And then the theorem is that this automorphism is independent of the loop. It's independent of the. Well, let me put it this way: if two loops are equivalent, then you get the same automorphism. Okay, so the theorem is that equivalent loops define the same automorphism. And so you get a map from the edge group, right? From the equivalence classes of edge loops. And so thus, there is a map from the edge loop of the barycentric subdivision of the nerve base at U0 into the automorphism group of this. Okay? So if F is locally constant, and this map is called the monodromy. The monodromy of this open cover, right? And then its image is the monodromy group. Okay, monodromy, this locally constant pre-sheaf on U. All right, so I'll prove this theorem next time. And then I will relate it to the ray spectral sequence. Okay, yeah. So next time will be our last class.